Bismillahirrahmanirrahim. Dear viewers, today we will design shear wall, spandrel with boundary element and coupling beam. In previous tutorial, we have seen some different ways to design shear wall. Now here we will design the shear wall and we will check if their boundary element is required or not. If required, then we will design boundary element and we will design spandrel with coupling beams. So let's start. In previous tutorial we have seen our shear wall was like this. Here we will provide spandrel above the door of lift. So we will model that first, then we will go for design. Now we will make all story, then we will select this shear walls and then right click show selected object only. Okay, so now in our view, now we have shear wall only. Now we will go to plan view. Here we need to work here. So here if there is no grid line, we will draw grid one story. Select this joint, go to edit, add grid lines at selected joint parallel to X. Click on apply. Okay. Now we will modify grid. Here this one we will make it 2. Click on OK. Okay. Now we can work in elevation. Go to elevation to apply. Okay. If our lift door is 4 feet, that means 48 inch, then this side 21 inch, this side 21 inch wall will be there. So we will draw joint object 21 inch. Here negative minus 21. Click on OK. Okay. From plan, go to GB. Here draw wall. In this time we will not assign auto peer ID. We will do it manually. If there is opening inside wall, then we cannot provide peer levels automatic. So now here one story, we will draw our wall like this. Then go to elevation 2. This portion also we will draw wall. Then go to elevation 2, apply. Up to grade beam there will be no door opening. In ground floor there will be opening for lift door. So these 3 we will replicate to next story. This is reference plan. If we want to create door opening here, we can do one thing. Draw a reference line. Here to here. Then this line I will move it down. If the door height is 7 feet, that means 84 inch. Our floor height is, here we can see, 144 ground floor height. So 144 minus 84, it will be 60. So this one we will take it down minus 60 inch. This frame, this we will divide them. Intersection with visible joint objects on edges with selected frame object. Apply, close. Now this portion we can delete, and this reference frame also we can delete. Here this portion is spandrel. We can assign this shell, spandrel, add some names for click on OK. Assign apply spandrel. This one can be assigned as modify, add some names, add 3 4 P2, this one P3, this one P4, this one P5, this one P6, this one P7, and this one P8. Okay, now we can replicate this to next story, first floor roof. Okay, here we can see the story height 132, that means 12 inches less than ground floor. So we can move this joint 12 inches up to keep our door 7 feet. Okay, now this joint, this joint, this joint, and this joint we will move up 12 inches close. Now go to define peel level. More peels we will add P9, P10, P11, P12. Okay, then define spandrel levels 7, 8. Click on OK. We can keep this P4 same because this height is 7 feet, this height also 7 feet. We can change this speeds. This one assign shell speed level P9, P10, and this one assign spandrel level, make it 2. Go to story, second floor roof to stair top, click on apply. Here this portion stair top height we can see 96 inches. So if our lift does not continue up to stair top, that means at the roof level, it will end at this level. So here we will not keep opening. So this one we can delete, and this one delete. This joint we can move from here to here and go to stair top level, wall SW8. Okay, now go to elevation 2, apply. Here this wall P level, before we have assigned P10, now we can assign P11, this one P12, this one P13. Okay, after finishing our modeling, we can go to select object type, wall, select, go to assign shell, wall auto mesh option, meshing size we will see here. Previously we have meshed our walls in 24-inch size, so we will make it same for this new walls. Click on OK, apply, close. Now we will go for shear wall design. Before that, run analysis. After finishing the analysis, we will go to design, shear wall design, view, revise preference. We will design our shear wall according to SCI 31808. Click on OK. Then go to define, load combination, add default design combination, concrete shear wall design. Click on OK. Click on OK. Then go to design. From here, go to select design combination. Here we will see the auto generated load combination according to the code has been assigned for design load combination. If it is not assigned here, if these combinations are listed here, then from here we have to select all the load combination for shear wall. Then click on this arrow, it will be in the design combination side. Click on OK. Then we can go for start design or check for our shear wall. Here it is showing the design result. You can see here, go to here, display design info, is longitudinal reinforcing. Here all the reinforcement required are shown according to the design, and we can see spandrel long bar from here also, top and bottom, left side and right side of the spandrel. We can see spandrel shear reinforcing also like this. We can see pier shear reinforcing also like this. So from this result we can design our shear wall and spandrel. In previous tutorial we have designed this side and this side shear wall. Now in this tutorial we will go to design these shear walls, these piers and this spandrel. Here is the Excel sheet. This Excel sheet we have seen before also in previous tutorial. We can select the shear walls, go to design, shear wall design, view or revise, peer overrides. Here we have selected uniform reinforcing method. Here another option is also available, simplify tension and compression. We will design these walls in uniform reinforcing, so we will keep same as it is. In previous tutorial, here in my channel you can see shear wall or lift core design in Etabs. We have done shear wall design. Now we will check our shear wall if there is a boundary element needed or not. If boundary element is needed, we will design boundary element, and for spandrel we will check coupling beam is required or not. If required, then we will design spandrel with coupling beam. So here if this side, if boundary element is required, then we will provide the boundary element along this full length. We can check here boundary element, check here boundary element is required, so this portion we will provide boundary element. First we will check the other portion of shear wall in longer side, this side. Go to elevation 2, elevation 2, apply here. Here we can see the reinforcement percentage required or ratio 0.03. 3.2% reinforcement required here. We can design this portion with higher thickness of shear wall, then this reinforcement percentage may be reduced. Here we can see 2.644% rebar is required. Now for this wall we will go for design, apply. Here required reinforcement is 11,329. We will open our Excel sheet. We will go for design, this one. This wall thickness is 200 millimeter and length of this wall is, from here we can see, length 2413 millimeter. We will type here 2.413 meter. Height of this wall 3.658. Required reinforcement is here 11,329. If we provide rebar 14 milli dia, then required spacing is coming 65.58 millimeter. Usually we do not provide this much closed spaced main rebar. We will try to keep the spacing above 100 millimeter. So we will select main rebar 16, then it is coming 85 millimeter center to center. So our thickness of wall should be increased. Here if we select the objects, wall, select this, select properties, slab section, here stair, deselect, okay. Then unlock this one. We will change the shear wall thickness, assign shear wall section, shear wall 12 inch, that means 300 millimeter, apply, okay. Then we will run analysis again. After finishing the analysis, we will run design again. Here design finished. Now we will check reinforcement. Display design reinforcing, apply, okay. We can see the reinforcement ratio. It is coming 0.0179, that means 1.79%. Before it was above 3%. Longitudinal reinforcement 15,122. Here we will provide that value 15,122. As our thickness is now 300, so required spacing is coming 64 millimeter center to center. If we increase the diameter, then it is coming 100 millimeter center to center. We will provide 100 millimeter center to center. This is our main reinforcement design. Required shear reinforcement is, we will see, shear reinforcement 875. We will provide 10 millimeter die bar for transverse reinforcement or shear reinforcement. Required spacing is coming 179.52 millimeter. We can provide 175 millimeter center to center. Here 175, or we can provide usual spacing is 150 millimeter center to center. Now we will see if there is boundary element needed or not. Okay. Now click on this shear wall, review the result. Boundary element check. Boundary element is required because the stress limit is 5.52 MPa. Our stress coming more than this one, 5.65. 6.01. Our stress limit is 5.52 MPa. That means 0.2 into a prime C. Here we can see our Excel sheet. First we can discuss about the basic of boundary element. This is one plan of shear wall with boundary element. Here width of boundary element more than the thickness of shear wall. We can provide width of boundary wall same as thickness of shear wall. So here length of boundary wall LB, width of boundary wall WB, length of web LW. Here if we draw the stress strain diagram, then somewhere at C distance there will be neutral axis. From this neutral axis we will get the length of boundary element, because our code says we have to take boundary element larger of C minus 0.1 LW. That means length of wall, this one, and here C by 2. So larger value of these two will be taken as the length of boundary element. Okay. Now here another things, when our shear wall is having axial load and lateral force that is giving us shear along this direction, it will have a deflected shape like this. This face will feel tension and this face will feel compression. Okay, so according to this tension and compression zone we can provide boundary element. Here this axial load P or PU we can divide into two parts to apply on boundary element, PU by 2, PU by 2, and the acting moment for lateral force, if we consider MU, having the lever arm L prime, it will give us two forces, that is mu by L prime along this direction, mu by L prime along this direction, which is compression. So net force is coming Pu by 2 minus T on this boundary element. The net force is coming Pu by 2 plus C or Pu by 2 plus mu by L prime. When the lateral force is acting along opposite direction, then this face will feel compression and this face will feel tension. So we will design boundary element for the governing net force. So now come to our, we have considered strength of concrete here 4000 psi. That means here if we convert it, 4000 divided by 145, that means 27.58, or we can write here 27.6 MPa. Fy we have provided 60 ksi, which is equivalent to 413.7, like this. Axial load we will take from here, axial load Pu here 4925.6, 4925.6, and moment 60.72, 60.72. Okay, and length of shear wall thickness all we have taken here, that is coming automatically here. If we want to check the stress manually, we know the formula. Stress is Pu by Az plus minus M by Z. Z is sectional modulus, that is giving us the formula Ig by Lg by 2. Gross length of shear wall and gross moment of inertia of shear wall divided by 2. Using this formula we will get the stress 6.9 MPa. But this is not the final stress, because here we have to provide the boundary element length according to the requirement. Okay, here if we provide 6.9, then required length of boundary element is coming 854.5. So here we can provide 855 millimeter boundary element length. Then here our stress is coming 6.26. This is the final stress for our manual calculation. You can see the stress from Etabs result. Here maximum stress is 6.01. So here we can write 6.01. We can continue with this value, or we can take our manual calculated value 6.26 MPa. So this stress is more than our allowable compressive strength, which is 0.2 F prime C. Here we can see 5.52 MPa. In Etabs also 5.52 MPa. Okay. Now our boundary element length is 855 millimeter, and width of boundary element, if we do not take it larger than the thickness of shear wall, then we will provide the same width as the shear wall thickness, 300 millimeter. So this is our boundary element length and width. Now we will go for rebar design. Here axial load on each boundary element. The load is now divided into two parts, Pu by 2, as we have seen here, Pu by 2. Okay. So lever arm here, center to center of boundary element 1.558 meter. Here it is in millimeter. So calculate each side load from moment. Mu by L prime is 39 kilonewton. So resultant load on one boundary element is this one, and on another boundary element is this one. One time summation, one time deduction. Seen here, this side Pu by 2 minus T, Pu by 2 plus C, this one. Okay. So Pu max is coming this one. Gross area of the boundary element is this one. Strength reduction factor 0.65. Here you can see the formula to find out the required steel from the load capacity. Alpha here is 0.8. So AST required is coming this one. We are getting required reinforcement is this one, where rho is coming 1.21%. Minimum rebar to be provided 1% for boundary element. So this is okay. So design reinforcement is coming from here, this one and this one. It is taking maximum reinforcement from these two values. So if we provide 25 millimeter dia bar, then the required number of bar is coming 6.3. If we provide, as our length of boundary element is 855, so we can increase the number of bar, we will reduce the diameter of rebar. So here it is coming 9.84, so we can provide 10 number of 20 millimeter dia bar. Along length of boundary element, if we provide 4 number of bar, then along the width of boundary element, the number of bar will be 3. As width of boundary element is 300 millimeter and length of boundary element is 855 millimeter. So here in this direction we can provide 4 number of bar, or if we provide 5 number of bar, then this side we will provide 2 number of bar. Okay. So boundary element main reinforcement design finished. Now we will design boundary element shear reinforcement. Moment, maximum moment, it is taking this value from this sheet, this one, 60.7 kilonewton meter. Okay. Shear maximum factored we will take from here, ultimate 676. 676. Okay. Now from this required parameters we will get the design of shear reinforcement. Now from the other required parameters, from here we will get the design reinforcement for shear. Now here confinement perpendicular to LB, that means length of boundary element. Extra tie legs or cross tie at number of alternate bar 2, that means here alternate bar means, for example, this is the arrangement of rebar along LB. So alternate, if it is 2, then here is one leg, these two skip, and here another leg or cross tie, then these two skip and here another leg. In this way, if there we provide the alternate number is 1, then it will alternate only one bar. Here one, here will be one cross tie, this skip, then another here, this skip, then another here, like this. So here if we provide 1, then number of leg is coming 3 along LB direction. Okay, so spacing of tie leg A6 is 403 millimeter, which is more than 14 inch. If it is more than 14 inch, then cross tie will be mandatory. So we will increase the tie, we will make it 0. That means all the main bar will have the tie bar. So number of leg is coming 5. Then here the A6 spacing is coming 201. Now it is not mandatory. That means if the spacing of tie is 201 millimeter, then in between them no need another extra cross tie. Now spacing of transverse tie bars along vertical surface of the wall according the code is coming 75 millimeter. That means minimum dimension of boundary element divided by 4. Dimension is 300 millimeter, so divided by 4 is coming 75 millimeter. So from this specifications we are getting governing tie spacing 75 millimeter, and confined width we are getting here BC. That means from here to here distance is the confined width. Okay, so this BC 1 will be 805 millimeter. It is coming from the length of boundary element minus 2 clear cover, both side clear cover. So required transverse or shear reinforcement is coming 363 millimeter square using this formula. If we select the tie bar dia is 10 millimeter, then the provided reinforcement is coming 393 millimeter square. So this tie bar at spacing of 75 millimeter with leg of 5 legs, the provided reinforcement will be 393 millimeter square, which is more than the required. So it is okay. Along this direction our leg is coming, there we have determined 5 leg is coming. So here 10 millimeter dia bar 5 legged stirrup at 75 millimeter center to center. Now we will determine the leg this side 1 2, here it is showing 2 leg. Along this direction we will determine now how many legs are required. Here if we provide extra tie legs or cross tie at number of alternate bar, if we provide 0, here another option number of leg is coming 2, but consider extra tie legs except perimeter hoops. Here it is no, because we have only 2 bar in this direction, main bar. So only 2 leg we can provide. So extra cross tie will not be provided. If there is 3 4 number of main bar, then we can provide here yes. Okay, so if it is no, then here number will be automatically 2. So spacing of tie leg is coming 125 millimeter, then cross tie not mandatory. Spacing of tie bars according to our is 75 milli, same 3 specification. From this 3 value we are getting maximum spacing 75 millimeter. So confined width BC2, that means the confinement width along this direction excluding the clear cover is coming 250 millimeter. Required shear rebar is coming this one using this formula. So if we choose the tie bar is 10 milli at 75 millimeter center to center distance with 2 leg, then provided reinforcement is coming this one. So this is okay. According to the design calculation we are getting this detailing. If our boundary element looks like this, that means width of boundary element is similar to the thickness of shear wall, then it will look like this. So our boundary element design for main river and shear reinforcement finished. Now we will go for spandrel design. Here we can go to the elevation 3. Now for spandrel we can see the spandrel reinforcement, spandrel long river. Here for example we will design spandrel for this one. Here two values are showing, one is top river, another is bottom river. These values are for left end, these values are for right end. Okay, so from it we will determine the top and bottom reinforcement. Here we can see this one, this is our spandrel. We will design top river, bottom river, then horizontal face river and vertical river, that means shear reinforcement for spandrel. Then if diagonal reinforcement required, then we will provide coupling beam. Now here our Fy, F prime C all are coming from previous sheets. Required river area for flexure at top we will see here. From here also we can see, or already we are getting here 1600 millimeter square. So here we will provide that value, this one. If we provide 20 millimeter dia bar, then top river is coming more than 5 number, so we have to provide 6. If we provide 25 millimeter dia bar, then 4 number of bar is enough at the top portion. Okay, and bottom side also same, 1600 millimeter square. So if we provide 25 millimeter dia bar, then 4 number is enough at the bottom. Okay, now we will design spandrel shear and skin reinforcement, that means vertical and horizontal reinforcement. Thickness of spandrel, here we will provide 300 millimeter as per our thickness of wall. Clear cover 25 millimeter. Height of or depth of spandrel, here we will check. Here we can see depth 1524 millimeter, 1520 millimeter depth of spandrel. Vertical river required from design result. See here result. Vertical river 2377.89, 2377.89 millimeter square per meter. If we provide vertical bar size 10 millimeter dia and leg of bar is 3, then required spacing is coming 99 millimeter. But prescribed maximum spacing from these three values or three equation, d by 5, 12 inch or 6 into dia bar, it is coming 150. From these four values, minimum value is 99 millimeter. Okay, so here if we provide 12 millimeter bar, we can provide like this with smaller spacing like 75 millimeter center to center spacing. And now horizontal river, this horizontal rivers same like we provide torsional river at the middle face of beam. Here for spandrel we need some face river or skin river, which is called as horizontal river. So required reinforcement, here we can see horizontal 525. Here 525. If we provide 10 millimeter dia bar, then required spacing is coming 299. Prescribed maximum river is 8 inch, that means 200 millimeter. So governed spacing is 200 millimeter. So S provided 200 millimeter. So here we have got our design reinforcement for spandrel. Top 4 notch 25, bottom 4 notch 25. Here these two leg vertical river dia bar at 75 millimeter center to center spacing. Here C horizontal rivers in both faces, 10 millimeter dia bar at 200 millimeter center to center spacing. Now If diagonal rebar is required, that means coupling beam is required, then we will design coupling beam. Diagonal reinforcement mandatory, yes. See here, required reinforcement is 1807 millimeter square. Here maximum value we have to take 1807. If we provide 25 millimeter dia bar, then required number of bar is 4. So we will provide here top 2, this side bottom 2. That means 4 number of diagonal bar will go here, and it will have rectangular tie bars in both directions. Now coupling beam transverse reinforcement to be designed. Select tie bar dia. Here confined width of coupling beam, that means this one, this BC, confined width of coupling beam. Here clearly you can see this is the coupling beam portion, this is BC, confined width. It is coming from the value of width of spandrel, then minus the horizontal bar of shear wall or spandrel, minus main rebar or vertical bar of shear wall, then keep some space in between these two. We can give 10 milli or 15 milli or 20 milli, so that value also will be deducted from this width. Then ultimately we will get BC value, and accordingly we have to provide the detailing. So here BC from this calculation is coming 177.5 millimeter, and AC also confined height of coupling beam, as top 2 rebar, bottom 2 rebar, total 4 25 millimeter dia rebar is required for coupling beam. So this direction BC and this direction AC will be same. If here 6 number of bar is required, then the arrangement is like this, then AC can be larger than BC. So here as it is 4 number of main bar is required, so we will provide the AC same value 177.5 millimeter. So from this we are getting a spacing of tie 75 millimeter. Here 3 specification, one is TS by 4, one is 6 into diameter of diagonal rebar, and another is maximum 6 inch. Now governing spacing is coming 75 millimeter. Provided spacing or provide spacing, here we will provide 75 millimeter. And gross area of coupling beam, assuming the minimum center to center around the confined area is coming this one. Gross area of coupling beam including the clear cover around the confined zone, and confined area of coupling beam, here we are getting this into this one. And required shear reinforcement for vertical side ASA is coming this one, using this formula, and or another formula this one. So comparing these two value, governing required rebar area is this one. Select number of leg for tie bar along AC. If we provide 2 number of tie bar, then it is saying increase the tie dia or leg, because the provided rebar is less than the required. So if we increase the tie rebar dia 2 leg, then it is okay. So for shear reinforcement for tie bar along AC, then this is the design: 12 millimeter dia bar, 2 legged, 75 millimeter center to center spacing. This one we have checked with AC. Now we will check the leg along BC. Required rebar, here it is coming 175. If we provide 2 leg, then provided rebar is this, so this is coming okay. This will be same because BC and AC dimension is same. So both direction we have checked. Now we have got the rebar detailing for coupling beam shear reinforcement like this: 12 millimeter dia bar at 75 millimeter center to center spacing, and the main bar is 4 number 25 millimeter. So in this way we can design shear wall with boundary element spandrel and coupling beam. This Excel sheet you can get it from my website decodebd.com. Then go to skill development resources. Here are the resources for this one: shear wall with boundary element, spandrel and coupling beam design. This price for Bangladeshi buyers 1200 BDT, for international buyer 15 US dollar. So from here, if you need to get this Excel sheet, you can buy this one. So thanks for watching. Stay tuned for more upcoming important tutorials.
Press the bell icon on the YouTube app and never miss another update.